Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The proof of Fermats' Last Theorem, culminating in Andrew Wiles' landmark 1994 publication but significantly informed by his earlier 1990 work on modular elliptic curves, stands as a monument to human intellect. The journey to this proof, spanning centuries and involving a vast array of mathematical concepts, is a compelling narrative of intellectual perseverance and the interconnectedness of seemingly disparate mathematical fields. This essay embarks on a detailed exploration of Wiles' 1990 contribution, particularly as it lays the groundwork for the ultimate proof, critically examining the claims, arguments, and methods presented within and tracing their implications within the larger mathematical landscape. It will not attempt to reprove the theorem, instead focusing on assessing the integrity and impact of the original claims. Section 1 Introduction to Elliptic Curves and Modularity. The initial stages of the 1990 paper serve to establish the foundational concepts required for the subsequent arguments. A central idea involves elliptic curves, defined by cubic equations taking the general form of y squared equals x cubed plus x plus b, where 4a cubed plus 27b squared does not equal 0. Wiles establishes that these curves, despite their seemingly simple algebraic definition, possess a rich geometric and arithmetic structure. He emphasizes the group law on elliptic curves, where points on the curve can be added together geometrically, forming an abelian group. This algebraic structure, combined with the analytical properties arising from viewing elliptic curves over the complex numbers, allows for the development of a complex theory. He then pivots to modular forms, functions defined on the upper half-plane satisfying specific transformation properties with respect to the action of a modular group. These modular forms are characterized by their Fourier expansions, providing a link to number theory. A pivotal claim is the assertion that every elliptic curve is modular, specifically, that there exists a modular form whose associated L function, a Dirichlet series encoding arithmetic information, matches the L function of the elliptic curve. Section 2 The Taniyama-Shimura conjecture and its significance. Wiles elucidates the Taniyama-Shimura conjecture, now known as the modularity theorem, which posits that every elliptic curve over the rational numbers is modular. This conjecture, initially met with skepticism, became a cornerstone of modern number theory due to its profound implications and unexpected connections between elliptic curves and modular forms. Wiles argues implicitly for the theorem's importance by outlining its connection to Fermats' last theorem. Fermats' last theorem states that there exist no positive integers a, b, and c that can satisfy the equation a to the n power plus b to the n power equals c to the n power for any integer value of n greater than 2. Phrase elliptic curve, defined by y squared equals x times x minus a to the n power times x plus b to the n power, provided a crucial link. Phrase suggested that if Fermats' last theorem were false, then this elliptic curve would be non-modular, contradicting the Taniyama-Shimura conjecture. Wiles' claim is that proving the Taniyama-Shimura conjecture, at least for a large class of elliptic curves, would disprove the existence of the Frey curve and thus prove Fermats' last theorem. He does this by demonstrating that the Frey curve has properties which are incompatible with modularity. Section 3 Galois representations and deformation theory. A significant portion of Wiles' 1990 work is dedicated to the study of Galois representations. These representations map the absolute Galois group of the rational numbers, which encodes information about field extensions, into groups of matrices. The particular Galois representations of interest arise from the action of the Galois group on the torsion points of elliptic curves. The n torsion points are the points on the elliptic curve which, when added to themselves n times using the group law, result in the identity element. Crucially, Wiles introduces deformation theory, a powerful tool for studying how Galois representations change under small perturbations. He claims that the deformation rings, which parametrize these deformations, can be understood through their relationship to Hecke algebras, algebraic structures arising in the theory of modular forms. The core idea is to show that the deformation ring is isomorphic to the Hecke algebra. This is sometimes referred to as the R equals T theorem, where R represents the deformation ring and T represents the Hecke algebra. This isomorphism would provide a vital connection between the arithmetic of elliptic curves and the analytic properties of modular forms. The use of Galois representations opens new vistas onto the modularity problem, providing a language in which to relate the two seemingly disparate mathematical objects. Section 4, Understanding Hecke algebras and modular forms. Wiles delves into the properties of Hecke algebras, crucial for establishing the R equals T isomorphism. Hecke algebras are algebras generated by operators acting on spaces of modular forms. These operators, known as Hecke operators, encode important arithmetic information about the modular forms. Wiles establishes that the study of the Hecke algebra can be reduced to understanding certain congruences between modular forms. These congruences relate to the behavior of the Fourier coefficients of modular forms modulo a prime number. He argues that the structure of the Hecke algebra is intimately related to the structure of the deformation ring, allowing him to translate information about modular forms into information about Galois representations, and vice versa. This connection is fundamental to his approach. Further, he asserts the importance of understanding the minimal primes of the Hecke algebras. These are prime ideals which are minimal with respect to inclusion. They play a central role in understanding the structure of the Hecke algebra and in proving the R equals T theorem. Section 5, The crucial case of semi-stable elliptic curves. Wiles focuses on proving the modularity of semi-stable elliptic curves, which are elliptic curves satisfying certain simplifying conditions on their reduction modulo primes. Specifically, semistable curves have either ordinary or multiplicative reduction at each prime. This restriction simplifies the analysis considerably. He argues that by proving modularity for semistable curves, he can leverage results from other mathematicians, such as Ribot's level-lowering theorem, to deduce Fermats Last Theorem. Ribot's theorem states that if an elliptic curve is not modular, then a related elliptic curve with simpler properties, namely, lower conductor, can be constructed that is also not modular. Wiles argues that by showing modularity for semistable curves, one can prevent the infinite descent that would be required to violate Fermat's last theorem. The focus on semistable curves reflects a strategic decision to tackle a manageable subset of the problem first, with the understanding that this would have significant implications for the broader conjecture. Section 6, The R equals T theorem and its implications. The heart of Wiles' argument lies in the proof of the R equals T theorem, a pivotal result connecting deformation rings and Hecke algebras. He claims that under certain technical conditions, the deformation ring representing deformations of a Galois representation is isomorphic to the Hecke algebra acting on modular forms. This theorem allows him to translate arithmetic information about elliptic curves, encoded in a deformation ring, into analytic information about modular forms, encoded in a Hecke algebra. Wiles uses sophisticated techniques from commutative algebra and algebraic number theory to establish this isomorphism. He particularly uses results on the structure of local rings and on the behavior of Galois representations. The proof of the R equals T theorem is a highly technical achievement, requiring a deep understanding of the interplay between arithmetic and analysis. It is the linchpin of his approach to proving the modularity of elliptic curves. Section 7, The analytic class number formula and its role. Wiles employs the analytic class number formula, a powerful tool in algebraic number theory, to establish crucial estimates needed for the proof of the R equals T theorem. The formula relates the class number of a number field, a measure of the complexity of its arithmetic, to the value of its Dedekind zeta function at 1. According to Wiles, it allows him to control the size of certain Selma groups, which measure the obstruction to solving certain arithmetic problems. By bounding the size of these Selma groups, He obtains crucial estimates on the size of the deformation rings and Heck algebras. The inclusion of the analytic class number formula underscores the deep connections between different areas of mathematics that are brought to bear on the problem of Fermat's last theorem. Section 8. The role of Iwasawa theory in the proof. Iwasawa theory, a branch of algebraic number theory that studies the behavior of arithmetic objects in infinite towers of number fields, features prominently in Wiles' proof. Wiles contends that through it, he was provided with a powerful tool for studying the structure of Selma groups and Galois representations. Iwasawa theory allows him to relate the behavior of these objects in the infinite tower to their behavior at finite levels. This relation provides crucial information about the structure of the deformation rings and Heck algebras. He argues that one may establish results about the R equals T isomorphism through consideration of the corresponding structure over an infinite tower of fields. The application of Iwasawa theory highlights the sophisticated techniques employed in the proof and the deep connections between seemingly disparate areas of mathematics. Section 9. Dealing with the error and subsequent corrections. Wiles initially announced his proof of Fermat's last theorem in 1993. However, subsequent scrutiny revealed a gap in his argument, specifically in the proof of the R equals T theorem for certain cases. This error centered on the use of Wiles systems, a powerful tool for studying arithmetic objects. Wiles, with the help of Richard Taylor, was able to overcome this difficulty by modifying his approach and incorporating techniques from other areas of number theory. He claims that this revised approach led to a complete and correct proof of the R equals T theorem and thus of Fermat's last theorem. The discovery of the error and its subsequent correction underscore the rigorous standards of mathematical proof and the importance of collaboration in mathematical research. Section 10. Impact and legacy of Wiles' work. Wiles' proof of Fermat's last theorem had a profound impact on number theory and mathematics as a whole. Wiles argues that it cemented the importance of the modularity theorem and spurred further research into the connections between elliptic curves and modular forms. The techniques developed in the proof, such as deformation theory and the R equals T theorem, have become fundamental tools in modern number theory. The proof also demonstrated the power of interdisciplinary research, bringing together ideas from algebraic number theory, algebraic geometry, and representation theory. Wiles' achievement has inspired a generation of mathematicians and has had a lasting impact on the development of the field. The completion of the proof signaled a pivotal moment in mathematical history, representing a triumph of human intellect and a testament to the power of mathematical thought. Section 11. The modularity lifting theorem. Wiles' work is now understood to have inaugurated a new era of proof techniques in number theory centered on what is termed modularity lifting. This involves starting with a modular Galois representation, that is, one arising from a modular form, and then demonstrating that any deformation of this representation is also modular. Wiles effectively proved a specific instance of this broad principle. He claimed to have generalized the approach so that it might apply to a wider class of problems, particularly lifting modularity from residual representations to integral representations. This has led to important advances in understanding the Langlands program, a far-reaching set of conjectures linking number theory and representation theory. Section 12. Alternative approaches and refinements. While Wiles' proof is considered the definitive resolution of Fermat's last theorem, subsequent work has focused on refining and generalizing his techniques. Alternative approaches, sometimes involving different variants of the R equals T theorem or the use of different types of modular forms, have been explored. Wiles argues that these alternative approaches offer new insights into the underlying mathematics and may lead to further progress in related areas. The exploration of different approaches highlights the richness of the mathematical landscape and the ongoing quest for a deeper understanding of number theory. Section 13. The importance of computational verification. Given the complexity of Wiles' proof, computational verification has played an increasingly important role in ensuring its correctness. Complex computations are used to verify certain key steps in the proof, such as the calculation of Selma groups and the verification of congruences between modular forms. Wiles' claims were supported by computational evidence. The reliance on computational verification underscores the importance of collaboration between mathematicians and computer scientists in modern mathematical research. The use of computers allows for the exploration of complex mathematical structures and the verification of theoretical results. Section 14 Future Directions in Modularity Research. Wiles' work has opened many new avenues for research in number theory and related areas. Wiles believes that one promising direction involves extending the modularity theorem to other contexts, such as elliptic curves over number fields other than the rational numbers, or to higher dimensional analogues of elliptic curves, such as abelian varieties. Another direction involves exploring the connections between modularity and the Langlands program, a vast web of conjectures linking number theory and representation theory. Wiles claimed that the proof of Fermats' Last Theorem has provided a blueprint for tackling other long-standing problems in number theory. Conclusion: Andrew Wiles 1990, preliminary work, and the subsequent definitive proof of Fermat's last theorem represent a watershed moment in the history of mathematics. Wiles' contributions not only solved the centuries-old problem, but also brought together diverse areas of mathematics, including elliptic curves, modular forms, Galois representations, and Iwasawa theory. His meticulous construction of the R=T isomorphism and rigorous analysis of semistable elliptic curves showcase the profound depth and elegance of his approach. Though an initial gap surfaced, the eventual resolution, achieved with the assistance of Richard Taylor, further demonstrated the resilience and self-correcting nature of mathematical inquiry. The lasting impact of Wiles' work extends beyond the specific result of Fermat's last theorem. It has inspired a new generation of number theorists, provided powerful new tools for attacking other problems, and underscored the deep interconnectedness of different mathematical disciplines. Wiles' work stands as a testament to the power of human intellect and the enduring beauty of mathematical truth. The work demonstrates that the journey of mathematical discovery may contain unexpected turns, but the pursuit of truth remains paramount. Furthermore, it suggests that collaboration and the willingness to adapt are vital to overcoming obstacles and achieving breakthroughs. It illustrates the power of abstract thought and the intricate beauty of the number system. The ultimate proof stands as a testament to mathematical perseverance, innovation, and the enduring quest for understanding the profound depths of mathematical reality.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.